Today we're going to talk about some special qualities that carbon has, and then we're also going to talk about something known as resonance. Up until this point, we've said, yeah, just throw that double bond or triple bond or whatever it might be in anywhere, but we'll see the real story today. So starting with carbon bonding, what we end up seeing is that it does have some unique properties. First of all, it's always going to be the central atom. So for example, on your homework that you had just last night, you had a molecule that looked like this. And we knew right off that hydrogen could not be your central atom because it can only hold 2 electrons. But when you were looking and trying to figure out should carbon or should nitrogen be your central atom, you voted for carbon because it is the least electronegative. Well, what we're going to see is that it's even easier than that. It's always going to be the central atom. It also tends to undergo bonding to itself, and that's a term known as catenation. And like we said, it's always that central atom. It bonds to itself. It can form these chains. So it's going to get 4 bonds to it. It's not going to have lone pairs attached to it. And then this last little tidbit is nothing new. Just always make your most symmetrical option available. And our first example, let's do this doing the needed available shared. I'm going to start with my most symmetrical skeleton. I've got 6 hydrogens, so I'm going to do them like this. Note, I have to do, and I'm not finished there, I can't put a hydrogen over here. That wouldn't be possible because this hydrogen cannot hold any more than the 2 electrons that it already has, or that it's shooting for, I guess I should say. So we can never bond anything additional to a hydrogen. It can only have that one bond. So there's our most symmetrical skeleton. We have our needed, available, and shared. As far as needed, that's going to be 28. As far as shared, it's going to be 14. Take a second and count those up and make sure you get that. Also, another little note for you. Whenever we're looking at just carbons and hydrogens, your available is always, always, always going to be half of your needed because carbon, for example, it needs 8, but it's only got 4. Hydrogen needs 2, but it's only got 1. So it's always going to be half, meaning 14 are going to have to be shared, which equals 7 bonds. Suppose you wanted to say 14 minus 14 to get your number of lone pairs. 0 lone pairs. So 7 bonds. 1, 2, 3, 4, 5, 6, 7. Pretty easy, no lone pairs at all. I'm going to go through this really quickly. Next one, these are just carbons and hydrogens again, so let's not even worry about doing needed and available and shared. You can go ahead and do that, but chances are it's not going to help you a whole lot with a lot of these thought processes. So first one we're going to look at C3H8, also known as propane. Oops, I didn't mean to do that. Let me remove those. Okay, so we've got our hydrogens. I'm doing 8 hydrogens. Okay, so now we just want to make everybody happy. So you start with single bonds everywhere. Always to your central atom of carbon. Carbon tends to bond to itself. It makes chains of carbons right there in the middle. And I look at this and I see everybody's happy. Carbon has 4 bonds in every situation, and hydrogen just has that 1 bond. You could do your needed, available, and shared and convince yourself you would get the exact same answer that way. So a little bit trickier, C2H2. Well, that's the most symmetrical I can make it. So now I go in and I throw in my single bond everywhere. Something's not right. The carbons don't look happy. They're only feeling 2 bonds each. So now I can make 3, 4. So we've got a triple bond in that middle between the carbons. Notice it's got to be there. We can't have it with the hydrogens because, again, hydrogen can only hold those 2 electrons. Okay, so now we get to something known as resonance structures. And before we truly get into those, let's think about the length and the strength of the bond. And this is very intuitive. If you've got a single, double, and triple bond, well, which one of those would be the longest? The longest one would be the one that's going to be the weakest. It's going to be the one that's not holding it together as tightly. So our general principle is that the more bonds between 2 atoms, the shorter the bond length. So if you have something like a triple bond, it's going to have a pretty short bond length. And as far as strength, the more bonds that you have between 2 atoms, the stronger that bond's going to be. So in other words, it's going to take more energy to try and break apart that bond. And this bottom part, don't worry about anything about memorizing here. This is just a little bit of some examples for you. By the way, you have a typo here. This should be a triple bond. And what we end up seeing is that for a single bond, you have the longest bond, and it's also the weakest. And as far as the triple bond goes, you're going to have the shortest, and it's going to be the strongest. So that's just what we summarized up ahead, or up above. Okay, so now we're getting into what this really means. Well, up until this point, if we were going to draw the carbonate ion, which is CO3 with the -2, first thing we do, most symmetrical skeleton, I'm just going to do something like this. I'm going to go ahead and throw it in brackets with the charge, just so we don't forget later on. When we calculate the needed, available, and shared, you've got your 32 as needed. For available, you've got 18 for your oxygens, plus 4 for your carbons gives you 22, plus 2 more for the charge, so that's going to be 24, meaning there's 8 that are shared, which means 4 bonds, which means you're going to have to throw in a double bond somewhere. So I'm just going to do that. Let's go ahead and put the lone pairs where they need to be. Notice that carbon does not have any lone pairs. And notice that this bottom oxygen only has 2 lone pairs, not the 3 lone pairs like the others. Okay, that's a totally acceptable answer up until this point. But now what we realize is that the truth is, it's not just like that. We have to draw all of the resonance structures. So I'm going to go and draw it in that double bond in other positions. And let me just jump over here. And give everybody their electrons, their lone pairs. And what we see is that actually the double bond is not just right there, it's not just right there, it's not just right there. What we're going to end up seeing is that it's really located in all of those spots. So here's where we see it, these molecules, none of these are actually how the ion exists. Instead, it's a combination of those 3 structures, or a hybrid. The hybrid that's mentioned here is something like blue and red make that purple. But another way of thinking about it is a ceiling fan. Each one of these, you can consider each one of these structures as being like the blade of a ceiling fan. But when that ceiling fan starts going fast, it's kind of this mixture, this blend of all of that stuff. So that's what we're thinking is going on here. Well, how do we know this happens? And the question, or the answer is, if we were to look back at one of these structures, I'll choose this middle one right here, it doesn't really matter. How many different bond lengths and strengths would you expect to be able to see? Well, you'd expect to be able to see a single and a double. So you would expect, if there was just one of those resonance structures, you would expect to see 2 bond lengths. Well, we only see 1. That's what's actually observed when we that ion is tested. So the bond length, if the bond length of just a single carbon-oxygen bond is 143 picometers, and the bond length of a double bond between carbon and oxygen is 122 picometers, what we see is just one bond length that's somewhere in between those values. Don't worry about trying to average or anything, but that's what we get, and that is all we have.